Well, thanks for that very generous introduction. Especially given that my job is simply to pose questions to the speakers who are the big brains here and they're going to do all the hard work. I think it's really important to make this fun and effective for the audience to get engaged and ask some questions. So I'm going to try to sort of wet the pump or prime the pump and get things started. And then I hope that people from the audience will step in. And I've also invited the panelists to pose questions to one another, of course. So, don't put it all on me. It's important for me to share the work. I'll ask a question which I started to ask to Fei Li earlier, and which Chris Atkinson has also been pushing a little bit over the last few days, or maybe the last few decades. And I guess, so computer vision has been tremendously inspired by reflections on human perception. And that seems to be a little bit different for visual learning when it's applied to manipulation. Fei mentioned Alison Gopnik's work on babies. Alison's my cousin, by the way, so that's an internal plug. But her work is very non-computational, and Chris ranted against how misleading it is to think about biology and what a terrible thing it would be for us. And so I guess the question is, do you think biological inspiration and the limitations of biological manipulation has held us back? Are there things to offer that we haven't tapped? And has it kept our view narrow? Because a lot of the work in manipulation that we look at, even though it doesn't use completely biomorphic systems, still tends to have a fundamentally human scale paradigm attached to it. There's not a lot of people doing manipulation at a very small or a very large scale, although there are some exceptions. So is biology a good inspiration for vision-based manipulation or a bad one? Is it misleading, or is it going to help us? And anybody can take this, but Russ is nodding, so I can, if I have to identify one person, I can poke on him.
Well, I was nodding because Dieter undid his mic. He was going to go.
What?
No, okay. I thought.
Oh, because I unmuted. No, I can.
You unmuted. Oh, Dieter's got it. Good. No, okay. Well, I'll try. So it made me, when you asked that just now, it made me think of Matt Mason going around and giving his talk just after Berkshire Grey came public, and Chris had just made a big to-do about after years of your talk about the mechanics of manipulation, suddenly you're talking about suction and what happened. And I thought Matt's view of that was actually really good. I'll try to channel it, I don't know, but basically he thinks that we've been too fixated on the human hand, for instance, and that it's held us back from very reasonable and actually incredibly useful tools, suction being one of them, but maybe the entire tool use possibilities of the kitchen. It's very rare that you're doing something super dexterous in the kitchen without a tool in your hand. So I think in some ways, maybe looking at ourselves has actually confused us or limited the possibilities.
Anybody want to take the other side of that?
I must say, yeah, is it the other side? I don't know. I must say the good thing is, as roboticists, we are often actually pretty pragmatic, right? Like, which means there might be some inspiration take from humans, and I agree with the hand, but a lot of work is, of course, just with these, let's say, these normal grippers. I think, again, people are often just worried about getting things to work, right? Which even not taking too much inspiration maybe from humans. Where I think inspiration from humans is good is just if you don't take it too literal, but just think about the kind of capabilities that humans obviously bring to the table, right? Like the lifelong learning kind of capabilities, generalizability. So these are kind of the questions we, I think, constantly need to ask ourselves. How much do we overfit to certain settings, or will the techniques that we pursue ever have these properties that we clearly see in humans, where we can constantly improve, and even if you throw a new task at us, we just play around with it and then suddenly we can solve it.
Anybody else?
And say that I agree. It's not a different position. I agree. Actually, I was thinking about suction that Russ brought up. I was thinking of it in the context of the Amazon picking challenge, right? And we saw big disparity between different teams. But I do think we have an overfixation on vision maybe, and not enough focus on tactile manipulation. And that is maybe even a disconnect from biology that maybe we want to be more inspired by biology. And it's been a focus. It's not that we're ignoring this area. It's just hard. to build such systems, but we rely on vision so much, right? Versus as humans, we can reach sideways or even behind us or into a bag and come out with the right object. And we're still really lacking in this area.
I just say that there's no reason in my mind that a robotic system should mimic what a human does. People can't shoot light out and measure how long it takes to turn. They can't communicate instantaneously with other agents without confusion. There's just a lot of things that robots can do that people can't. And so to design our systems motivated by the capabilities of humans, I think doesn't make sense to me. And then I'll even go further and say that there's a lot of robotics that is, humanoid because the affordances of the world are with humans. But if we got to a point where, robots were doing lots of things, then we would redesign the world. And we're kind of in this in-between place where like self-driving cars work with vision because roads are set up with road signs and lanes for people. But we should eventually migrate to a situation where there are beacons on the road that are designed for computers, and, things like that. Anyway.
It's good.
I think
I can add something to this. Oh, Thomas, are you still going?
No, I'm sorry, I'm done. I should have muted.
Greg, earlier referencing Alison Gopnik, and I would say maybe what I take away, what sticks most with me from her talks is two things that are maybe a little tangential to how we're looking at that here, which is I believe she has this graph showing in some sense level of intelligence achieved as a function of the amount of time you get to spend in childhood. And so the thing to be taken away from that seems to be that if you get a lot of time to play and to do non-useful things, maybe as a robot also, then in the end, maybe you can get to a other level later. And then the other thing that keeps coming back when I see her talks is this notion that somehow kids set their own goals. Like, you don't need to set any goals. They keep busy setting goals that they just imagine, and they're good to go. And it seems like at that level, there's a lot of things we have completely no idea how to exactly incorporate that. Maybe we should not, but we don't really know very well how to make, robots have a long childhood, or robots set their own goals to then hopefully learn other things in the future.
Can I comment on that? So that, again, that's
Yeah.
a very human-centric comment, because another difference between people and computers is that computers get to leverage all the data that any computer has ever seen, and so there are no children robots in the steady state. Every time you build a new robot, it downloads everything known by any other robot ever before. And so yes, I guess when learning a new task, you need to explore and all that, but really this idea that you're going to be like an infant discovering how to grab things, I think that's again true in this transition period where we're learning how to grasp, but in a steady state we would have been able to with all the training data that's been captured before, and it's different.
I think we're all captivated by the idea of a machine that can learn from, tabula rasa, starts with nothing and actually learns to be competent. And yet in the long term, I guess we're going to expect to see robots all over the place where you take them out of the box and they've already learned at the factory, or they've downloaded that learning. And maybe that's a bit of the tension between the direction that Peter's talking about and what you're raising, Thomas.
Can I interrupt for a second? We have a special guest, Ken Goldberg from UC Berkeley. Ken is very kind to take the place of some other speakers who cannot join today. And we're very fortunate to have him. And I didn't prepare an introduction for him, but I guess I don't need to, because his work has been very inspiring to the field, and he had his research spans across robotic manipulation, robot learning, cloud robotics, and many other topics. And I guess, and I guess Ken will, Ken is also very cool, one of the coolest robotics, because he's also, I think he has also contributions in some of the art domain. So I would love to hear like Ken's opinions about some of the topics today.
Thanks, Kwang, for putting me on the spot there. By the way, I love your background. No, I'm actually here to really listen. I was very curious about what the others have to say. So I'm really just a fly on the wall here, but I'll jump in if there's something I have to add. Thank you.
All right, I've thoroughly lost track of where I was in my head there. Feel free to jump in, anybody. I guess we were talking about this dichotomy between ab initio learning and downloading everything in advance, and which side of that fence you want to be on. Russ, which side of the fence do you want to be on? Do you want to like get a robot that's going to start from scratch?
The steady state, but I do think we have to figure out how to get there, and so I think the transition is maybe today's problem. But I think anytime we can look ahead to the steady state, I think we are wise to do so.
Okay. So I put a couple of questions up that some of you saw earlier. I'm going to take a different question. We can always come back. But this one actually got some support, at least a little bit of support. And the question was, why robotics manipulation has apparently been much less fruitful than some other areas, such as pure computer vision or autonomous driving over the last little while. Is there some underlying reason why manipulation is fundamentally harder or something else? I'll put out one hypothesis just to get you started. Now, I think one thing that might be true is that manipulation and vision-based manipulation in particular crosses the boundary between, I think, mechanical understanding, things you learn in mechanical engineering, and also straight computer science and information theory. And so it's got a more hybrid flavor, maybe, much as the robotics does relative to some of the pure computer vision problems. Is that a factor?
I think certainly that the hardware is one of the problems, right? When it comes to having good articulated robot, whatever, hands manipulators, but also, as Sonia said, for example, on the sensing side, right? Touch sensors, I mean, there's nice ones coming up, but it's still extremely impoverished. And then, of course, I mean, if you think about self-driving cars, computer vision, there's a huge community working on that. And the manipulation community is now, I think, growing very rapidly, but I think so far it's not that many people who actually used to work on this. And also the problem space, it's just very, very difficult, right? Because you suddenly have that physical interaction with the environment, whereas cars, it's mostly not to touch things, right?
So Dieter, you're saying that fewer people want to manipulate things with the robot historically than want to drive a car down the road?
Few people working on it.
So
Yeah.
those factories at like some place or other, there's no factories using robot arms to manipulate stuff?
Oh, I was focusing on the research community actually. So I think now, okay, so in that sense, of course, there is now, I think, finally a very strong pull from the manufacturing industrial community, right, towards smarter manipulator, as for example, like Peter's company, Covariant, is showing, right? So I think there's also hope that that will really help drive the robotics research community forward to do better work and maybe building on this progress that's been driven by industry also for their own research.
So do you have a sense for what the biggest single challenges in vision-based manipulation? Is there a favorite thing that you think the community has to rally around? I guess everybody gave a talk on something, so don't just say my own work is the thing. But if you could move the needle somehow or shift, you've got, on the order of 75 people listening here, how do you want to push them?
Okay, Russ has been unmuted for a while, but he's nodding. So this is not trying to push anybody, but it's a comment about what's hard. And I think we don't understand contact well enough. And that's one of the challenges, right? And that's really the weakest link in this whole very complicated pipeline that you've already mentioned. If you're just driving or just doing navigation-based research, you are interacting with the world, you're closing the loop, but your effect on that world is much more predictable than when we're really dealing with contact forces. And I don't think we have simulations that are quite good enough yet. We just are not able to model that. And I think that's making progress slower than otherwise it would be. but I'd love to hear Russ's take on it because he's been.
Yeah, I would push back on that. I heard Ken's take on that actually at the sim to real debate, which was awesome. Yeah, I think sure it's hard, but we know how to make simulators, and there are some. You know, Ken gave the example of the pencil that's indeterminate. The Coulomb's laws are not actually complete or fully determined because things aren't actually rigid bodies. I agree with that, but we can do a pretty good job, and I don't actually think the fidelity gap there for a carefully used simulator is, I mean, you can use simulators and set their parameters badly and get strange results and do wrong things. But I think we have good enough contact models these days. That's not where I would put the blame.
So where is it?
I mean, the original question, I guess, like, why is manipulation behind or something? I don't know if it's, yeah. I mean, I feel like these things are punctuated evolutions, and it just happened that computer vision went, and then everybody invested in, and self-driving, had its watershed moment, and everybody, and suddenly people were pouring in money, and I think manipulation's maybe ready to go. It's like on the verge. I think we needed perception to happen more for us to even imagine the problems we're trying to tackle today. So the manipulation work of 10 years ago looked very different because we just didn't even think about trying the kind of problems that we can try today. But I don't know. I think it'll just happen. We'll have a couple of key results, and then Google will buy something, and everything will just go like that.
That doesn't always work out so well, eh?
Well, I'm the least qualified of all of us to make this comment, but I'll give it a shot anyway. So I think the reason that manipulation gets held back is because it's hard to compete with the human hand. Human hands are just amazing at all the things they can do and the manipulations they can do, and in compared to, say, self-driving cars, we're competing with human drivers who have a steering wheel, a brake, and a gas pedal. So I just think that the range of applications that manipulation can beat low-cost human labor are smaller than in some other fields.
I mean, the human hand is a high bar, but the human visual system is pretty damn impressive too.
But there, I think we can compete. It's more the physical manipulation would be my impression. But again, I'm the least qualified of all of us to say that.
Maybe that's what Sonia meant too. I didn't. So I think it's not the laws of contact mechanics or our ability to simulate them that's hard. But I do completely agree that we haven't mastered the dynamics of interaction or something, right? So we know how rigid bodies interact in simple ways, but I think there's laws of intuitive physics basically that we're just missing, which are govern the interactions of complicated piles of objects and laundry and stuff like this. And so in that sense, I think we are still very far from having what we need.
Yeah, I bet somebody in this group is actually involved in working on that kind of simulation, but they're not speaking up. So Ken, in case somebody missed your sim to real comment, Russ referred to it. I'm guessing that there's a bunch of people listening in who might be wondering what in the world he's talking about. Do you want to just give a quick recapitulation?
Sure. I mean, it's just an example I give where if you want to understand the indeterminacy of manipulation, just take two pencils, and you take the first one and lay it on your desk, and then push it with the second pencil. And then try and repeat that again, exactly the same initial conditions, and push it across the table. And it is inevitable that it's going to end up in very different configurations. And the point is that it's essentially undecidable where it's going to end up because of microscopic surface friction and contacts. And one small grain of sand under there will make all the difference. So you don't have to go to very complex scenarios. I mean, it's sitting right in front of us. And yet humans have learned how to adapt, and even animals. I have a dog now who's pretty good at pushing her bone around the floor. So that, I think there's a very small margin for error, that the models, the functions here are discontinuous, right? So this very small difference in the position of my fingers can cause a difference between me dropping the object or holding it successfully. So there's a lot of nuance here. And I think it's also in deformation is a very important thing, because one thing we don't model very well, at least in my experience, is the deformation of contacts. And that seems to be very, very helpful for human holding things. So if we have we put on rigid gloves or something like that, we're much more clumsy. So I think if we start to understand that, but that adds a whole other layer of complexity and indeterminacy onto the interactions.
That seems to suggest maybe that if we had better hardware, we'd have a much easier time. Like even though a hand might seem more difficult to control, having tactile is higher dimensional, but it might actually simplify the problem a lot once we have access to that.
I still think you can go to the store, the toy store, and buy one of those little grippers with a claw on the end and do so many things in the home that we wish we could do with our robots. That of course I want the hardware to be better, but I don't want to blame the hardware today. I think we have untapped potential.
I think that might be related to the fact that we've been looking, or we've been neglecting for a long time really the importance of, let's say, visual closed loop control, right? Like constantly using visual feedback during these actions. So when Ken says it's extremely unpredictable, right? Context and all of that, that's important if you want to do open loop control, right? But if you constantly reassess kind of what the state of the object is and how you're holding it and all of that exactly, then things might become much easier. And we just have to, we're in the process of figuring out how to use that kind of information.
I'm going to give a shameless plug for a paper. There's Sharon Song has this paper called Grasping in the Wild, where she collected a whole bunch of data with the thing that Ken just showed, grabbing things in the house, and then has a closed loop control algorithm to learn how to grasp things from that training data. Just was accepted to RA letters and IROS. Sorry, shameless plug, but on topic.
Okay.
I'm going to take a couple of questions from, oh, sorry, Dieter, after you, I'll take a couple of questions from the audience.
Just one quick other point, and Russ is right, also the comments on and Ken on soft contacts, right? And that is something that I think now the good thing is when you look at the main groups working on physics simulation, like Russ's team, Mujoko, Physics Flex at NVIDIA, they're all kind of starting to look more into simulating those kind of contexts. And I think that will make things hopefully also easier even, right? It's harder maybe on the modeling side, but on the control side, it might make things much easier in the end.
Mm-hmm.
But I have to believe that if we depend that much on the details, even though I'm investing a ton of energy trying to understand those details, I think if in the end, if our controllers depend on the nuances of those contact models, then they're not going to work. It can't be that sensitive. We have to like get it right so that we can learn to be robust about it.
Well, that came out in the discussion yesterday too, right? Where on the one hand side, we should separate that. Yes, it's good if we can model the details, that would be great because then we have the simulation. But what the robot then learns from that doesn't have to replicate that, right? The robot should just learn policies that are robust, as you said. I agree. And that doesn't have to be any accurate modeling underneath, actually.
And I think if you don't see the non-robust policies, it's hard to know what the robust ones are going to be. So Senthil Palanisamy asks, are we lacking good material science collaboration in the robotics community? Are we restricting ourselves to construction of human-level systems with materials that we have presently in the market? If more research on materials is applied on novel materials, will we be able to reach the dexterity of human fingers more readily, for example? Any takers? Do we need more material science research? You can turn it into a nice binary question.
Isn't the answer always yes?
It's certainly yes that we could, like if you have more, we'll use it. I guess the question is it a bottleneck?
I think the rigid body assumption is a huge bottleneck, and that it's baked in sort of the way we think about pose as a representation was the first thing we went to, even though we think it's not right anymore, and that was a big topic for today. But just even the way we engineer things, everything's built to be precision and rigid, and I think that is somehow a trap that we've fallen into. And I think soft robotics, you know, but even just breaking away from starting with rigid body state estimation and the like, I think that has to just work its way through the whole system, and it'll change the way we think about controlling end effectors and building hands. I completely agree with that.
So when I was a grad student a long time ago, my supervisor gave me the book by David Marr to read, which is a wonderful book, and he's a wonderful author and a super smart guy. And it caused me to waste years of my life because I think I went down pathways that, I mean, many people have suggested that Marr's entire sort of paradigm was misleading. It's very arguable, but that's just the intro to my question. My question is, are there perils for the community, like things that would be seductive that we shouldn't do? And if you don't want to take it in that form, are there mistakes that you've made where you say, oh man, I wish I hadn't done that thing? You know, negative examples for us. Maybe this question is a negative example. So I'm gonna tell my students to go home tonight and start building robot hands out of whatever tools they have around the lab. That can't possibly be a good idea. You don't want to give me any other bad ideas, eh?
I'm not sure about, I can give, but I don't think, I'm actually a fan of what you might call mistakes or things like that, right? Because that's how we really learn, and that's how we move forward and see limitations. So, and Russ also already hinted at that, for example, the notion of 60 pose of objects, right? On the long run, I think most of us agree that this will not be the solution to many of the problems. It will still be super useful maybe in many industrial applications or so, but if we want to go, let's say, for general robot manipulation tasks, maybe going more in learned representations, of course, is the theme that is more promising on the long run. That's one thing we clearly realized, that even if you do a very thorough job, for example, on 60 pose estimation, it still doesn't solve manipulation. It's still a hard problem even after that. So going more down the learned representation route is clearly the right way to go in the long run.
My dog's freaking out. I have to change locations.
I'll take a stab and say, I don't know about materials, but I am a big fan of using kind of non-traditional sensing to supplement other forms of sensing. So through this collaboration with Charlie Kemp at Georgia Tech, we've been using spectroscopy for material recognition. Usually that's been tactile, right? This is a little handheld device you hold up to the object that performs a scan, and it's great, right? And it's super easy. The robot can pick up a sensor, sense some stuff. You can imagine it being built into the end effector, tiny. It's actually very, very small. Build it right into the finger. The robot could obtain materials without needing tactile sensing. And so, you know, it's not quite related to the original question, but I think thinking outside the box, and it really comes back to our earlier discussion about bio inspiration. We don't always have to, I think, limit ourselves to biology. And I think the more creativity we have aim towards multiple modalities for sensing, the better.
That's great.
Taste and touch, and I'm sorry, and sound, and all the other senses that we ignore. Olfaction, right? Is that a trap for biology, or is that something that we should be bouncing on?
I must say there's not that many tasks that at least we are looking at right now where I say, if we had only solved olfaction, then that problem would go away.
You know, I took a tour of a kitchen, you know, the expert chef kind of kitchen once. And he says, in this kitchen, we train our chefs to use all 5 senses when they're cooking. They taste, they smell, everything. And you can't cook the perfect, whatever it was, fish fillet, unless you're using all 5 of your senses. And I wonder if we're just missing the boat. Maybe it's because it's hard to simulate. I don't know. Maybe simulation was a trap, or maybe we shouldn't be restricting ourselves to the 5 human senses, like, you know, but there's probably more out there that we're impoverishing. I mean, we only put our tactile sensors like right here, even though we reach in and we touch with everything else, you know, in our hands, right?
I'm hoping that hardware limitation will pass as the technology becomes more affordable and more readily available and more robust.
I don't know. That's actually a question I have for the others on the panel. Is there and Russ just mentioned that, right? Like right now, even when you look at things like gel side, gel slim, or digit, all the different developments on the touch sensing, it's still mostly something on the fingertip. But what we really need is we want to have kind of touch sensing throughout the hand, soft skin and things like that. And my feeling is that's not gonna be solved within the next 3-4 years or so. I don't know, maybe people have some ideas on that.
So one of the issues with tactile sensors is they experience wear. Do you think that's an issue? I mean, it's an issue in some domains for sure.
It's a huge issue, yeah.
And therefore, what do we do about it? Just like, yeah, tough luck.
Well, there's a nice paper presented tomorrow, number 29, which actually has tactile feedback. So, I mean, there is some work happening in that direction that will be presented tomorrow. I think this is from Ted Adelson at MIT. So I think that's hinting at least at things becoming possible in terms of building the hardware. It's still just 2 fingers. It's, you know, it's not everything you want, but it's.
I'll mention there's some great work that's been done in the past where people try to grow a biological substrate, partially grow it, which then they can combine with electronics. I'm kind of hoping for a tactile sensor like that, although it'll be a little creepy at first. Let me ask a question from Danny. He asks, is the multimodality of solutions to manipulation problems a curse or a cure? If you won't answer it, I will. I think it depends. Like, I think for many problems where you don't need enough input, it might be, well, Dieter's going to answer. I don't have to.
Oh, no, I think I see this, of course, it's an opportunity, but again, I don't think these problems will just simply go away. As we see with these examples, how good people are with totally impoverished grippers, right? If you put that in their hand, or we did this work on DexPilot where a human can control an Allegro articulated hand to actually open a wallet and get a $10 bill out of it. And there's 0 touch feedback, right? It's just purely vision based. And it's pretty amazing. So I do believe touch sensing is going to be really important, and it would be great to have more of it. But I don't think there's any panacea out there where we say, oh, if we had that sensor suddenly, or if we combine these sensors suddenly, all the problems go away.
I want to add to that because Matt Mason, he always said, every sensor is going to add more complexity into your system. There's wear and tear, but it also means lots more signal and lots more noise. So then the other example is surgical robots. So if you watch a Da Vinci operation, there's no tactile feedback at all, and they're incredibly dexterous. And it's a very, very impoverished gripper, by the way. So it's the control. As Russ was saying, I think that you're right. That's an existence proof that you can do quite a bit in a very messy, wet, deformable environment with manipulating needles and suture. I mean, it's a really, really hard manipulation problem. So,
at the risk of contradicting myself, apparently, then, just to keep it interesting here. But
good, go for it.
I remember visiting Dieter when he had an early version of the Kinect before it came out, and I remember Dieter had this glow about him. He said, "This is going to be big. This is going to change things. And boy, did it, right? And no one would deny that the LiDAR, it just had this massive impact. And it wasn't that we couldn't do without it, because I think we can do a lot without perfect tactile sensing, but it's possible that we get, simpler algorithms work really well when you have super high rate, dense geometry coming in, right? And so I could totally see any one of those causing another watershed in robotics, but I do still think that the gripper is the existence proof that it's not, we don't have to wait for it.
So I'm gonna pitch a couple more from the audience too. I think some are long and some are short. Rika Antonova asks, if the pencil example is undecidable, then do we and can we have good enough simulators that Russ was referring to? And what are they that can handle the realistic simulation of manipulation with non-rigid objects for tasks that are more complex than just grasping a single object? Name one?
My version of the pencil. Just I feel like I'm talking too much, but maybe I don't know. Four-legged table, right? So here's the reason why it's indeterminate. Basically, you have a four-legged table, so you have four legs on the ground, four normal forces. They all have to balance gravity, okay? But they could be distributed in any way. If you have a three-legged table, if there's no moments, then you have enough constraints to say, I know what not only what the total sum of the normal forces are, but what those you can distinguish what the normal forces must be. But as soon as you have four, it's under constrained, and based on the laws of physics that we know, it could be any forces at any leg. Now, the Coulomb friction envelope is the fact it says that your frictional force depends on your normal force. So you push that table, you don't know how big your normal force is. It could be 0 on one leg, it could be, it could be all on three, it could be distributed evenly. So you don't know what friction forces, what are your maximum friction forces, and your table could spin, or it could go straight, or whatever. That's maybe the simplest example of it.
I guess on top of that, on a real surface, you may have non-uniform friction coefficient across the surface.
Oh, totally. That's what Ken was saying. Like, there's any one particle makes the real system not be undetermined. It's like it's our simplification that everything's rigid, that somehow is just an approximation, which doesn't always give unique solutions. It's a differential inclusion instead of a differential equation. We can still do control and robust control on differential inclusions. You just have to admit that the laws of the toy you're playing with here don't always go in one direction, right? And you can use feedback to stabilize it. So I think we can agree on equations, and we could agree if they're accurate enough for the task. And I think we can simulate those equations accurately with a good engineering. It's a lot of work, and we haven't done. I think a lot of the simulators don't have them implemented super well, but I think anybody can. Yeah.
Another issue that came up yesterday in Sim2Real was parameterization of the models. Like for tactile, you think that's an issue?
I think you could fit parameters. I think we know a little bit about how to estimate parameters. I think that if you depend on those parameters too much, you're dead. So, I think it is. I would love to do it better, but I don't think it should be a bottleneck yet.
Yeah, I mean, personally, I think actually collecting the data for complicated domains remains an issue, right? It's not unsolvable, but it's a lot of work. So I'm hoping somebody else will do it.
And we got some more experience also on, so that we have a paper at RSS on modeling the biotech hand, the sensor. And one of our research scientists, Yashnarang, he actually went through the process of building a full finite element simulation model of the SynTouch. And I didn't even know these kind of simulators existed with which you can do all of this, right? So they are amazing. They model exactly kind of the deformations, the pressure and everything. And the great thing is they have actually a small number of parameters then, and you can identify them, and you can actually be reasonably sure that they extrapolate really well beyond kind of the training data that you collect. Of course, the problem with respect to robotics, and if you want to use it for deep learning kind of things, that these simulators are super slow still. So the question is, how can we kind of find the right balance of coming up with simulators that are extremely fast? So we would like them to be multiple times real time, of course, that have the fidelity of these high-end simulation engines and can be identified. And of course, in the end also are differentiable, right? But I think we see a lot of good work coming out these days on differentiable physics simulation, and also these faster simulators. Like, as I mentioned, Russ's, NVIDIA, Mujoko, they are also becoming better and better, and also with deformable objects. So I'm very hopeful actually in that direction.
So Florian Skirty asks, what do you think are the most pressing shortcomings of current task and motion planning approaches? And how do you think, it's only halfway there, what are the current pressing shortcomings of current task and motion planning approaches? And how do you think about continually creating new symbols and incorporating them in grammars for control? And how do you think about better object discovery and incorporating perception into this framework? So shortcomings, symbols and grammars for control, and object discovery.
Dieter, you had TAMP in your title. I think that one's yours.
Well, I think one of the problems is still, even kind of with the work we've done, is really grounding them in the real world. And that means, on the one hand side, getting the perception so that you get exactly the state information that they rely on. And then often they still there's too much reliance on knowledge about like where objects are and things like that. But of course, again, there's a lot of research going on where people try to actually get away from this information. I had one slide on this kind of when the robot doesn't know where the object is, it can now try to find this object and things like that. So I think actually that the gap isn't that huge for many of these. It's just kind of the nitty-gritty details of the robustness in the real world. Also being it with the manipulation then itself, right? Like figuring out where the objects are and how to grasp them then.
Excellent. Okay, I think Animesh has one. He can ask himself.
Hi. I would go back to the original discussion. I think Tom mentioned this, Russ mentioned this as well. There's a lot we can do with very simple things, let's say suction or very simple grippers. And on the contrary, Peter mentioned this idea of we need robot childhood. And it's very cool. So I'll ask something a bit more sort of divisive. How do new students pick manipulation research problems? Should they work on stuff that is like doable within 3 to 5 years, aka the problem solving approach, like hook or crook, I need to solve this kind of argument. And it's not like I'm building a product for the industry, it's still research nonetheless. That's how manipulation research was for a very long time. Or the other way around, where like things do not work right now, that's fine. Let's do something simple, very simple, and it may be very long term. And hopefully there will be a watershed moment in 10 years.
I actually have a follow-up question on that, if I can ask a question beyond just answering things. I'm really curious on Russ's perspective on the kind of lessons learned in the DARPA robotics challenge that you did with your students, because that seemed like a great example of a wide open challenge. And I don't think anybody else here participated. You led a team and had the best entry with the humanoid in that challenge, I believe. And so very curious, because that seems, very ambitious.
Thank you. Jerry Pratt's team was the best humanoid team, but I think the DRC was awesome for us at the time. It took things that we kind of knew how to do, forced us to put massive engineering effort. It exposed me to the challenges of trying to field a robot that I had never, for me, it was just a fantastic experience. I think there was a complaint that the task, although it was broad, it sort of ended up that a lot of people took a pretty similar approach. So it, like many competitions have been criticized for, it narrowed the ideas, I think, a little bit. So I think Fei said it well. I think competitions can be great, and I think competitions can also derail some of the people that are coming up with a brand new idea. But you still have to answer Animesh's question, Peter.
So I think it's good to have a mix of things. I mean, as a student, you don't just do one project, but I think early on doing a project where you actually try to make something work, whether it succeeds or not, gives you a lot of intuition for what problems are still completely unsolved. And you might decide, imagine you work on something today, you might decide, hey, clearly what's, the big pain is hand-eye calibration. Like I'm supposed to do a paper on X, but I'm spending like 90% of my time on hand-eye calibration. And like, that should be a solved problem, but why am I doing 90% of my time hand-eye calibration? You might then conclude that maybe your next paper should be on hand-eye calibration, or maybe on real-time vision feedback that doesn't really rely on calibration. And so I think working on a problem that's somewhat hard, but then also realizing what are the unexpected things that really keep you busy is a very good way to get inspired about what you might want to work on next.
So in this specific domain, do you think you should start with a physical problem, like on a real robot or device, or do you start with a virtual problem? You of all people, Peter, might have a specific kind of answer.
I would say a real robot, because that's where the hidden challenges surface. In simulation, somebody is taking care of it for you. Everything's set up pretty much for success for you, compared to real world where nobody's helped you be set up for success.
And I would just add to that, Animesh, as you remember, back in the day in the lab, we would sit around and just talk about tasks that we would do as humans and that were interesting. Like I remember one we talked about peeling a banana. As far as I know, that's still unsolved. But those are,
and remember peeling a grape.
Grape, yes, that's a beautiful one. Or just picking all the grapes off of a you know, a bunch. I thought that was, I mean, because I think you could, if you just keep your eyes out, there's all these things out there. But if you demonstrate those, something like that, it is, if you're a student, I'm just thinking, you know, to get attention, to get your name out there, that would be interesting to solve something that hasn't been done. And think about those things, because I really think they're all around. There is so many tasks.
I'm going to take the unpopular view that manipulation is really hard, and there's just a lot of problems that need to be solved. You know, being around people. We already talked about the physical, the hand problem, so on and so forth. And so I think what will happen is that specialized robots will be built. So when we sort our coins, in a coin star, we pour them into a thing, and the gravity makes the coins fall through, and the different sizes sort them. And you could have imagined, okay, we have to do this as a humanoid with a manipulator and recognize the dimes versus the pennies and be able to pick them up and put them in the right bin and stuff like that. And maybe the banana peeling is like that too. Maybe there's a simple specialized device that can be built. And so I think that our world is going to have a lot of specialized devices that are simple and tuned to the problem, and not so many of these general purpose humanoid tasks. And I think it's great for research to think about how to do these tasks, but I think in practice they're too hard for an arm manipulator, and it would be better to do them in other ways.
I have, by the way, harvest grapes, but first of all, I think it took bunches, and I think it took them when they were not very ripe. So there has been some progress on the grape. Not the peeling problem, though.
Plucky.
I think Xiang has a question. Sorry, Ken.
Since we haven't talked about RL yet, I want to ask people's opinion on RL, especially for robotic manipulation. So I do a lot of perception with Dieter, but recently I also started looking at RL, but not just from image. I feel a little bit too hard. Maybe you can combine perception. For example, if we do RL from point cloud, second point cloud, or have some 3D information, but try to learn RL agents. Maybe that's what easier the task for complicated manipulation a little bit. So I would like to hear people's opinion on how can RL help, or is that a promising direction for robotic manipulation?
I think maybe part of the question, distinction between two questions here. One question is, how far can we push RL? And if you're just curious about RL as a discipline, manipulation is a really great environment because manipulation has combinatorial complexity. You can bring in new objects and the world changes for the robot. And so I think manipulation is a great test bed for RL. You can also think of the other way is, what's the fastest way to solve a manipulation problem? And I think then it's, if you're willing to spend a little bit of time as a person, you can give so many hints to the system. You can pre-train on Coco, whatever, to do segmentation. You can use a 3D camera to help, with the 3D understanding of the scene. And so there's a lot of things you can supervise or somewhat supervise by transferring from other problems that you can make a lot of progress on manipulation to have a head start compared to what pure RL would be able to do. Now, even if you do that, I think in the end, if you want to achieve very high reliability, you don't want to supervise all the way till the end. You probably want a system that can keep learning indefinitely while it's, let's say, deployed, while it's in the lab up and running forever, and keep collecting data. And so I think RL could play a pretty big role in kind of getting the last stretch there, where you wouldn't want to try to keep annotating forever to knock out the very last ones. In fact, you wouldn't know what to annotate because you wouldn't know where it's still failing. So I guess the very little bit of RL that I think you'll need at least is the notion of data collection in real scenarios and seeing failures upon which hopefully the learning system can improve.
That's really good. I think I'd like to suggest we're kind of, we started a little bit late, so we thought we'd take a couple of extra minutes. I have one more question I'd like to pose, and then maybe we could wrap it up there. I know at least one of the panelists has a commitment outside, maybe more than one. So Ethan Evan asks a follow-up question. He says, should we focus on the design of grasping an actuator and with it our sensing capabilities, or is it better to do what we can with what we have? And at what point do we reimagine the design versus continuing to solve the problem with current tools? Of course, there's many people with many styles, but you can ask, like, for you individually, do you think you should, would you like to actually make better tools, or would you rather work on the sort of computer science side of the problem? Better hardware tools, that is, I guess. Because some people are doing both, right?
The answer to that question for me personally is very easy. I'd rather work on the computer science side of it because I'm not qualified to do the other. And I also agree with Russ and others that there's a lot still to be done. There's a lot, there's a lot of headroom from where we are to what you could do with the current manipulators, current hardware.
I second Thomas, and I would say that there's so much work to be done in all of these areas that there's no one right answer. And you should really, if you're a student asking this, you should pursue your passion. Whatever excites you most, that's going to lead to the best results, because you're going to be much more creative and much more passionate about whatever you're working on. So all of these things need more work. Pursue whatever drives you and gets you out of bed in the morning.
Sonia, I think we need to add the caveat that you should stay to some extent within the envelope of the things you know something about. So if you've got lots of CS training, maybe stay away from designing the gripper, or yeah.
Well, I think that's a great space for collaborations, right? Where you can work with the people who do this kind of work as research, who see this as research, and then you can collaborate with them where you can bring in insights and they can bring in insights, and then you can maybe develop really cool solutions. But I of course agree, being still a computer scientist, that I also agree there's just so many questions that won't go away simply by building a different hand or so.
And one of the great things about grad school is, of course, learning a whole new domain that you didn't know about too.
But again, I sure hope people keep improving the hardware, because I think we need both for sure. I do a very little bit of that and a lot more computer science and controls, but boy, I think the dynamics of the manipulator matter a whole lot.
And since RSS is not only for computer scientists, so I think there might be many students out there who are really interested in that, right? And I wouldn't want to discourage them from doing this. So I think it's still a really cool area, especially because you see how much we want it, right? So clearly there's a market for that stuff.
I mean, there's almost two answers, one for faculty and one for students. I inherited a lab from Martin Buehler when he left McGill, and I got into underwater robotics as a result of that, and it changed my life, and it was really, really great. And so, like, it's really good to stretch your horizons a little bit, but maybe not every single day.
I mean, it's also maybe important to remember that I think we're at the very infancy of manipulation. We're only solving very, very simple problems, which are mostly like picking and grasping and the like. And I think the hardware we have is sufficient to do most of the things we're trying to do and still can't do very well in manipulation. I think as we get towards the limits of more interesting tasks, more complex things, then a dexterous hand is going to, we've already seen examples in just loading a dishwasher where, boy, I wish I had a more dexterous hand, and I think the more we push on the capabilities, the more the hardware is going to feel like a bottleneck again, and we'll be begging for those improvements.
So I'll ask one more question, and then I think maybe I'll say thank you quickly. But I think we all believe that human-robot interaction is becoming an increasingly important part of the game. And yet, so I guess the question is really, do you think that in the particular case of manipulation and vision-based manipulation, whether there are particular challenges in the human interaction side? Like, Russ, in your talk earlier, I asked about whether we lack vocabulary to express some manipulatory actions relative to how we can do it in vision. So is there any special HRI problem, or is it HRI just like more HRI? Just bring it on. We all have teach pendants, right? Where you can just move around the arm with a pendant, but that's pretty damn primitive.
I think HRI comes in on the side of teaching, learning from demonstrations. But one example we had with NVIDIA, we wanted to put like a robot system together, like a block stacking kind of robot, so that a person could just walk up to the robot and hand it a block in a natural way. And at the time I thought, object handover, that must be solved, right? People must have worked on that for decades, but by far not solved, right? It's amazing how hard it is to either receive or hand over an object to a robot in a really robust, open-ended, fluent way. So I think there's many problems of that style where we might think it's kind of solved, or it might not be that important, that when you actually look at it, there's a lot of research that we can still do.
Yeah, and I agree with Dieter. I also think a lot of it is not so much HRI as just H, right? We're just watching people and learning, you know, putting cameras on people's wrists and watching how they manipulate. Even that alone can give us so much data, right? And people have been looking at that. And then, you know, because as soon as you get to HRI and there's this active, you know, another agent acting autonomously in the example that Dieter said, that's an extra level of complexity that we otherwise don't have. So I think it's definitely a really, really exciting research area. And you can think of HRI as a whole or just the H part and what the H can bring to the R.
All right. Let me suggest we wrap it up there. I want to thank the panelists very much. This was great. You know, if the audience enjoyed this 1/10 as much as I did, then I hope then they must have had a really great evening. You were all really, really wonderful. I want to thank the organizers of the workshop as well. Kwan, David, Yuke, Dinesh, Animesh Garg, Linsun, Yuzhang, for putting the whole thing together. It was, I think, a very great day.
Dinesh.
Thank you all.